So we argued that for a sorted list, it's possible to get this algorithm down to a linear scaling, which is order of n. Uh, you know, uh, Before we start looking at the algorithm, let's make two observations. Assume that the underlying list is sorted, and the same problem that I'm going to look for the pair that adds up to a given target. But before we get there, let's make two observations. First thing first, let's say this is my list. Compare sum 1 and sum 2. Sum 1 is L0 plus L7. Sum 2 is L0 plus L8, which is basically L0, last but one item, and L0 and the last item. Now we can be 100% sure that sum 1 is less than or equal to sum 2. Sum 1 cannot be more than sum 2, and the answer is because the list is sorted, which means that L7 and L8 have a relationship in the sense that, L7 is less than or equal to L8. That's the definition of sorted. In fact, for first observation, you can just say L7 is less than L8, in which case this is a strict inequality. Similarly, if I look at two sums, which is L0 plus L8 versus L1 plus L8, we can be 100% sure that sum 2 here is less than or equal to L1, because for the same reason, the list is sorted and L0 is less than equal to L1, and hence sum 2 is less than equal to sum 3. So which means that sum 2 cannot be more than sum 3. In fact, this is the basis for going further. We can see how we'll use this to create the so-called two-pointer algorithm. Let me first describe it in words, and then we'll see a visualization. With this background set, we can now come up with an algorithm. We start with two pointers. Well, think of pointers as arrows that are pointing towards certain, index on the list, or if you want, simply the list indices, whichever way you're comfortable. Let's call them left and right. Set the left to 0, which means the first item on the list, right to length of L minus 1, which is the last item on the list. Something like this. So left is pointing here, right is pointing here. At this point, I go and find the sum. I call this as 0, L left plus L right. Now remember, the goal of the algorithm was to find if two values add up to a target. I found S naught. I find that S naught is larger than the target. Well, I know what to do because I am too large. I must reduce the sum, so that I get closer to the target. And the way that's going to happen, in fact, the only way that can possibly happen is I move my right pointer inwards, because remember, the list is sorted. This is the only way I can reduce the sum from the extreme sum that we had just found, right? So I move this inwards. On the other hand, if I find that, well, S naught is less than the target, well, again, the only way I can potentially increase is to move the left pointer inwards. So you see how we are smartly, moving the pointers, and how we are avoiding sums which are in fact quite redundant. Yeah. So I just move this pointer inwards. I keep doing this until one of these conditions happen. Either we find two values that add up to the target, and then that's done. The job is done there. Or we find that left pointer becomes equal to the right pointer, which means that there ain't any values which add up to the target. Let's see this with some examples. Let's say my target is 29, and here's my list 1, 2, 8, and so on and so forth. First, I find the sum 31, because 30 plus 1, which is, remember, more than the target. The only way I can benefit is to move my right pointer inwards. So that's come 29. 29 plus 1, 30, still more than the target, which is 29. So I move this to 21. I mean, that's just the values I've taken. 21 plus 1, 22. Now I have become smaller than the target, which means I'm going to take my left pointer and move it inwards. So that's 21 plus 2, 23. Smaller than the target still. So I say, okay, let's move left pointer inwards. That goes to 8. 21 plus 8, I am done. In fact, I don't need to search further. You can clearly see that, we are avoiding redundant sums. For example, with 1, we just found these three values because there's no point in searching 1 plus, let's say, 18. We know there's a better search to be done, which is to do 2 plus 21 here. And think about it, that's exactly what's going on. So we have found a target here. Um, the next scenario is where we do not find this target. So I started with a target of 35. So I look at, say, 31, which is, well, smaller than the target. So I say, okay, let's move the left pointer. So I go to 2. So 32, still smaller. I go to 38. That's too large. So I move my right pointer inwards. So that becomes 37. Still too large. So I move it further inwards. That's 29. Now it's too small. So I move this guy in. That is basically 30. Still small, so I move this guy in, that is 37. And at this point, we will terminate, because in the next step my two pointers will become equal. And this situation tells me that, look, I have not found any pair that adds up to the target. Very, very, very interesting. Think about it. As we discussed, this algorithm is making as many comparisons in the worst case as the length of the list, because we are avoiding redundant comparisons that was happening in the in the naive method, which was exhaustively searching. Remember, any algorithm becomes efficient if we make it do just the right amount of work for the problem at hand, maintaining the correctness. Correctness is obviously important, and this algorithm we see is indeed doing it, provided the list is sorted. So, very interesting. Think about it. Maybe take some use cases for your own. Take some, let's say, examples and work through it. You will get a good feel for it, and then we will come back and write the code. Do look at our website, www.ybyte.in. We have a lot of such content for you to learn Python, logic, programming, algorithms, and have fun. Take care. Thank you so much. Bye bye.